Welcome to the last introduction video for the Intel 8085. In the previous video, I've covered the software and the maskable interrupt INTR, which is compatible with Intel 8080 peripherals. You can find the link to the previous video in the upper right corner. In this episode, I will explain the remaining maskable interrupts and also the non-maskable interrupt trap. Just a quick reminder, a maskable interrupt like the INTR can be enabled or disabled in your code. The trap cannot be disabled. Well, there's one exception for that. Let's have a look at the interrupt priority of an Intel 8085 CPU. The lowest priority has a maskable interrupt INTR. A higher priority has a maskable interrupt RST55, then the maskable interrupt RST65 and RST75. The top priority of the interrupts has the non-maskable interrupt trap, but the highest priority has the hold request, which is typically used by a DMA chip. The DMA stops the CPU and will take over control of the system. Let's have a look at the vector address. For RST55 it's 2C. The CPU will do a call on the address 2C. That's 55 times 8. 65 is at address 34. That's 65 times 8. And for 75 it's 3C, 7.5 times 8, and for the trap it's the address 24, and the INTR, you will put the instruction on the data bus. So for the trigger type, for the trap it's a rising edge and high level until sampled. For the RST75 only a pulse is required to set an internal flip-flop, which generates the internal interrupt request. And for the rest, it's a high level until sampled. Back to the simulator, I have already entered the code. So the vector address for trap is 24, vector address for 55 is 2C, and for 65 is 34. And for 75 it's 3C. Our main program here will enable the interrupts and our endless loop. And for every interrupt routine I've for example, I've loaded the accumulator with the respective vector address, enabling the interrupt and returning from the subroutine. Nothing fancy, it's just to check the addresses. Maskable interrupts are all enabled and we are in our main loop. The INTR I have already explained it in a previous video. So 55 will jump to 2C, our program counter is at 44, so we will jump to 2C. Disabling the maskable interrupts. Unfortunately, in the simulator there's a bug. He also disables the non-maskable interrupt trap here, but normally this should be enabled. So in the stack you see a return address from the main program. Enabling interrupt again and returning. So the 65 will jump to 34. And a 75 will jump to 3C. And the trap will jump to 24. You see here, the trap shouldn't be disabled. and back in the main loop. So with the command enable interrupt, you enable all the maskable interrupts, and with disable interrupt, you disable all the maskable interrupts. Is there a way to individually enable, disable maskable interrupts? Yes, there is. With the instruction sim, set instruction mask, you can enable or disable the maskable interrupts individually. The sim instruction will use the value of the accumulator and set the appropriate masks. In the lower bit, there's a mask for the 5.5, and the next is 6.5 and 7.5. So if there's a 0, that means the mask, the interrupt is available, and if there's a 1, it's not enabled, not even with enable interrupt. MSE stands for mask set enable, so with a 0, the mask is not set or changed, and with a 1, the masks are set. With the next bit, you reset the flip-flop of the interrupt 7.5. As I have already mentioned, the 7.5 uses an internal flip-flop to register the interrupt. So with this bit, you can reset, you can clear the interrupt, you can clear the pending interrupt. So the next bit is a don't care bit, so you can put in whatever you want. Generally you will use 0, and the highest bit is a serial output data. So on your CPU you have pin 4, that's a serial out. So if you put a 0 in there, there's a 0, a low for the SOD, and if you put a 1, there's a high for the SOD. So the next pin, SDE, which stands for Serial Data Enable, it's used to disable the modification of the SOD pin, which means if SDE is 0, you can't change the output of the pin. And if SDE is 1, it will modify the pin with the value of SOD. This is a good example to use hex values. So you split your byte in lower 4 bits and upper 4 bits, and you put the respective hex value in there. So for example, you want to enable interrupt 7.5 and 5.5. What would be the value of the accumulator? Well, let's check first on the left side. So you want to change the serial output? No, that's a 0. You want to reset the flip-flop? No. So you will put a 0 here. And on the right side, so you want to change the mask? Yes. So that's at least an 8. And 7.5.5.5 enabled, so 6.5 should be disabled. 6.5 is 2, so 8 and 2 is 10. The value would be 0.8, and you will do a sim instruction and enable interrupt. Next example. Resetting 7.5 and enabling 6.5. So on the left side, reset 7.5, that's a 1. You don't want to mess with the serial out, so it stays 1. And on the right side, change the mask, that's an 8. And you want to enable 6.5, so 7.5 and 5.5 should be disabled. 8.4 and 8 plus 4 plus 1 is 13, so that's D. And next example, suppose you want to do a serial output to 1, so on the left side there's 8 for SOD, and you want to send it to the pin, you have to add the 4. That's 12. On the right side, you don't want to change the mask, so that's a 0. Last example, serial output to 0 and enable 5.5. So on the left side, SOD is 0, but you should send it to the pin, so that's 4. And on the right side, that's an 8 for mask set enable, and you have to disable 7.5 and 6.5. So 8 plus 4 plus 2 is 14. That's an E. It's time to play with the new command, sim. I will start with serial output pin. I missed main. Here it is. So I want to set the output pin 4, 0, and here in our loop I will alternate the output. I will do an exclusive OR with the most significant bit. That's 8. And do a sim. So the value is 40. Do an exclusive OR with 80. So that's C, that's 8 and 4. The sim send the output to 1. Alternating the most significant bit again. It's 4. Sim, output is 0. So the alternate functions correctly. It started raining outside, so with the command enable interrupt, all the maskable interrupts are enabled. So if you want to, for example, disable these 3 and enable only this one, you have to set a mask. Loading the accumulator with 0. The upper bit is, the upper 4 bits is 0 because you don't want to change the serial out. And you have the 8 for modifying the mask. And disable these 3, that's 1, and 2 is 3, and 4 is 7, 8 and 7 is 15, that's hexadecimal F. Doing the sim instruction. F, sim, and enabling interrupt. So interrupt is enabled because with enable interrupt this is always enabled. But these 3 have been masked out, so they are not active. Suppose you want to enable only this one and disable these 2. That's 1 and 4 is 5, plus 8 is 13. That's D. And you see here, only this one is enabled. So let's enter the trap here. And in the trap subroutine, at the end, you have again enable interrupt. Enable interrupt, and the interrupts are again enabled. But what will happen if, for example, you are in interrupt? Suppose we are in this interrupt. Well, thanks to the bug, we can't enable here. Let's modify the code a little bit. So it's a 6.5. Let's put an enable interrupt here. So we are in our interrupt, enabling the interrupt just for bypassing the bug. Suppose this one is disabled and you're entering is still in the RST65 interrupt, but now you're entering the trap interrupt. The other interrupts are now disabled, and if you exit this subroutine, it will enable the interrupt, which is not what we want, because we are back now in our 6.5 interrupt. So how do you know the status of the interrupt? How can you fetch the status of the interrupt flag before the trap interrupt? So the rim instruction comes quite handy. It will read the interrupt masks and put it in the accumulator. So the format is exactly the same as with the sim instruction. 0 means interrupt is enabled and 1 means it's masked. But the interesting bit is the IE, which stands for interrupt enabled. So 0 means interrupt is disabled and 1 means it is enabled. The other bits are just the state of the interrupts if the interrupt is pending. So 0 for no and 1 for yes. And the last one, that's the SID, that's the serial input data. So on your CPU you have your pin SID, and with the rim instruction you will read the value on this pin. Suppose the SID is 1 and the interrupts are all enabled. The rim would read 8, 8. Suppose the interrupt 7.5 is pending and interrupts are enabled except for 5.5. Rim would read 4, 9. Suppose there is no interrupt pending and the interrupts are disabled and the mask is set for 5.5, 6.5 and 7.5. So the value would be 0, 7. So let's try the rim in our main loop. Throwing a rim here. This I don't need anymore. And the rim reads a value 0 because SID is 0, and D 8 and 4 is 12 and 1 is 13. That's a D. So if I change the input value here, doing the next read, so it's 8D. If I change the mask here, to F. So all the RSTs are disabled. And reading the rim, so now it's F. Okay. And if you disable completely the interrupts, it reads just the masks. And the 8 is not set anymore because the interrupts are disabled. If you do a rim instruction in a maskable interrupt routine, the bit IE will be 0, because interrupts are already disabled. But the trap interrupt is individual. It also disables the interrupts, but preserves the previous interrupt enabled status. Performing the first rim instructions following a trap interrupt allows you to determine whether interrupts were enabled or disabled before the trap. But this works only for the first rim instruction. If you do a second rim in your trap subroutine, it will tell the interrupts are disabled. Okay, so in our trap subroutine, so before you enabling the interrupt, you have to check if they were enabled before. In this case, I don't need to save the accumulator. I don't need the value in the accumulator. Otherwise, you have to push it on the stack. So let's do a rim, and the only interesting value I want to check is the value 8. And if 8 is not set, you can just return the subroutine. Otherwise, you have to enable the interrupt and return. So this would normally work, but in the simulator it doesn't. It's doing a trap. Doing a rim, and you see here the 8 is missing. And there's also another reason, because I forgot to enable the interrupts. But even then, let's check it. So interrupts are disabled, are enabled. Doing a trap, a rim. So 8 is still missing. What will you do? Do an AND. So 0 flag is set because it's a 0. It will return from subroutine and won't enable the interrupt. So let's cheat a little bit here and doing enable interrupt. Okay, trap, enabling interrupt, doing a rim, and this time the interrupt enable is set. So an AND will resolve in 8, and 0 flag is not set, so it won't return on 0, but enable the interrupt and returning. Okay, let's jump to the real thing. So this is my setup. That's a MiniMax board with the Intel 8085 on it. That's a serial port. Here's the Arduino Mega 80K He has also a serial port, and he sends immediately the resets like trap, RST5 and 7.5. 6.5 is directly connected to this chip, and this one is a breadboard with an SN74HC595. That's an 8-bit serial in parallel out shifter, and it's connected to the data bus of the 8085 for the INTR interrupts. Sorry for the shaky camera handling and the bad lighting. This is a terminal for the MiniMax board with its ROM. I've entered the program at memory address 8000. So here you can see before the sim setting the accumulator with here 1. That means reset the flip-flop of interrupt 7.5, and 8 means set the interrupt masks, so all interrupts are enabled. Enabling interrupt, and here our famous main loop is doing nothing. And this one is used for the correct entry point for the interrupts. Because if you have for example, a trap interrupt, it's at address 24. This is not in memory, but in ROM. You can't change it. So I've already explained that in a previous video. So for example, the trap address is at address 24, and there in the ROM is a call to address 44, and here the next value is 24. So if you check at address 44, he's actually replacing the address. So here at address FFA0, he will put the 24 under FFFA0. And that's why I'm setting 90 here at FFA1, which is a high byte. That means at address 9024, there's a jump to address 8000C, and 8000C, there's the subroutine for the trap in this example. So let's jump directly into our main program. This is a terminal for the Arduino. I can send interrupts from here. So if I hit 5, it will send a reset interrupt. If I hit 6, it won't work, because 6.5 is not connected to the Arduino, but is directly connected to the serial port. So if I type a key here in the MiniMax terminal, it will say there's a key pressed, and that was interrupt 6.5. Back to the Arduino window, if I type here 7, it will do a reset. If I type T for trap, it's doing a hardware interrupt. I mean, they're all hardware interrupts, I mean a non-maskable interrupt. The first value here is the first rim. So here he knows the interrupt is enabled. And the second rim, he says, okay, the interrupt is disabled because we are on a subroutine. And here he will say, before quitting the subroutine, you have to enable the interrupt. I've implemented also other interrupts here. For example, the 2, it will put the RST2 command on the data bus, or 3 on the data bus, or 4, 5, or 6, or 7. 1 and 2 are used by the system. So if I enter, for example, RST0, it will just quit the program, because it jumps at the beginning of the ROM. I have to restart it here. If I type here 1, that's a breakpoint. RST1, it will do a breakpoint. It's also a debugger for the monitor program. Okay, works fine. So let me disable the maskable interrupts. That's at address 8008. And the code for disable is F3. Let me check it. 8008 disable. Okay. So when I enter here 5, doesn't work because interrupt is disabled. If I hit T for trap, that works. And now with the 0, you know interrupts are not enabled. 7, let me check the trap, and now you see there's a pending interrupt, and that's 7, because the flip-flop is set. Even if the interrupt is disabled, the flip-flop will be set. Other interrupts won't work. No. Okay. Even RST0 or RST1 won't work. The only one that is working is the trap command. Okay, let's put back this. That was FB, and change the value here. So resetting the flip-flop, and suppose we want to enable only RST55, so we want to disable 7.5 and 6.5. That is 8 plus 4 is 12, plus 1 is 13. No, plus 2, it's 14. 14 it's E. Yeah, because we entered the breakpoint before. I'm not sure if he likes it. Let's test it. Trap is okay. E is correct. And for the 6 is because the interrupts are disabled. So 14 minus 8 is 6. Five is working. 6 isn't. Well, 6 never works. Only in this terminal. And 7 doesn't work either. But if I do a trap now, you see there are 2 interrupts pending. That's a 4, that's a 7, and before I entered the keyboard here, that's RST65. That's why there are 2 interrupts pending. This one is working, also working. That was my last video of a long series. Assembler in general is not the most straightforward way to program, but in an 8-bit system it's often the only way if you need speed. An excellent way to learn assembler is to look at a lot of source code and try to understand it. And please don't forget to comment your source code, because after a short time, and when I say a short time, I mean it, it could be the same day, you can't remember what you did in there. The CPU is only one part. On top you have to understand the hardware of your system. Everything is low-level programming. If you're lucky, you can revert to well-documented and useful system functions of your operating system. If you get stuck, don't worry, take a break or even a longer break, or do something different before getting back to the problem. Thank you for watching. Bye bye.